Hello everyone, welcome back to my channel and welcome back to my series Learn with me Data Science. I am Anshika Verma and this is the 10th video of the series Dimension which covers the part Dimension Reduction. So dimension reduction is a technique in data science used to reduce the number of features or variables in a data size while preserving the most important information. This is done to simplify complex data sets, improve model performance, and reduce noise. Techniques like PCA, TSNA, and LLE are common used for dimension reduction. Uh, we are implementing dimension reduction with multicollineary and PCA. So first understand what is multicollineary. So multicollinearity occurs when two or more features in a dataset are highly correlated, causing redundant information and potentially destabilizing models. Dimension reduction techniques such as PCA principal component analysis can help alleviate multicollinearity by transforming correlated features into a smaller set of uncorrelated features. This improves model stability and interpretability. So now let's see dimension reduction implementation by multicollinearity. This is the code for dimension reduction. First, we demonstrate how to will identify multicollinearity in Python, and then we demonstrate how to apply PCA principal component analysis using Python. So firstly, we identify multicollinearity in Python. So firstly, we are importing the libraries. First, we import the Panda library for data manipulation, then NumPy for numerical operation. Then we are importing variance inflation factor function from states model for calculating VIF, and then we are importing the add constant for from state model for adding a constant term. Then we are creating a data sample data set which is data equal to x1 x2 and x3, creates a dictionary with three features with random values, and df equal to pd dot data frame in a data, converts the dictionary into a pandas data frame. Now we are introducing multicollinearity. So df x2 equal to df x1 plus np random normal, create a correlation between x1 and x2 by adding a small random noise to x1. Then we are preparing for data for VIF calculation. So x equal to add a constant df, adds a constant term intercept to the data frame. Now we are calculating VIF for each feature. VIF data equal to pd dot data frame function create an empty data frame to store VIF result, and then VIF data variable equal to x dot colons, assign the feature name to the variable constant, and VIF data VIF equal to variance inflation factor. Calculate VIF for each feature using a list comprehension, and then print VIF data, print the VIF result. So the output shows the VIF, which is variance inflation factor for each features in the dataset. For the constant term has a VIF of 7.33, which is not relevant for multicollinearity analysis, and for x1 is 8.68, indicating moderate to high multicollinearity, and for x2 it is 8.71, also indicating moderate to high multicollinearity, and x1 is 1.02, indicating very low multicollinearity. The high VIF value for x1 and x2 suggests that these two features are highly correlated with each other, which can lead to unstable estimate and inflated variance in regression models. The low VIF values of x3 indicate that it is not highly correlated with the other feature. In general, VIF value can be interpreted as VIF is less than 2 is no multicollinearity, VIF less than 5 and greater than 2 is moderate multicollinearity, and VIF, which is less than or equal to 5, is greater than or equal to 5 is multicollinearity, and VIF, which is greater than 10 or equal to 10, is a very high multicollinearity. Based on this result, we may want to consider removing or transforming one of the highly correlated feature, which can be x1 or x2, to reduce multicollinearity and improve the model stability. So this is the code and implementation of multicollinearity, and now we are moving to PCA, principal component analysis. So from starting, we are starting with the importing standard scalar class from skitlearn, and then we create a uh, and scalar equal to standard scalar creates a standard scalar object and scaled data. Standardize the data in DF by subtracting the mean and dividing by the standard deviation for each feature. Now we are applying the PCA. So from this library, we import the PCA class from skitlearn. Now moving to the application, PCA equal to PCA and component equal to 2 creates a PCA object with two principal component, and PCA component equal to PCA dot fit transform scale data, applies PCA to the standardized data and reduce it to two principal component. Now we are visualizing the PCA component by importing matplotlib.py as PLT library for plotting, and PLT scatter plots the two principal component against each other. PLT title plots the sets the title of the plot as PCA two components x label and y label. As always, sets the x and y axis label, and PLT.show displays the plot. So print explained variance ratio uh, prints the explained variation ratio for each explained component. So the explained variation ratio represents the proportion of variance in the data that is explained by each principal component. In this case, the output will show the explained variance ratio to be for the two principal. So the output it has given is 0.64 something and 0.33 something, which we can say uh, 0.7 and 0.3. It means that the first principal component explains 70% of the variance, uh, 70% of the variance in the data, and the second principal component explains 30% of the variance in the data. So this is the both implementation by in dimension reduction, and that's all for this video. We are in my next video. We are covering logistic regression modeling. Till then, keep smiling, keep exploring. Bye bye.